Hey super scientists, we're looking in your Intro to Chem lab notebook and we're going to be talking about Chem 5 gas laws today. So this is on page 9 in your lab notebook. As we talk about these ideal gas laws, we're going to be looking at how different variables relate to one another in reference to gases. So we're specifically looking at the state of matter of gases. So a couple of vocabulary terms that we need to review really quickly are volume first. So volume is going to be what you're looking at the amount of space basically that a substance takes up. So the volume of a gas is going to be the same as its container because a gas is going to take up the container, the shape of the container that it's in. For example, a balloon. If you have helium in this balloon, well, you can't see the helium necessarily, but you can see the container that the helium is in. So we see that the helium is taking the shape of the balloon. And at higher temperatures, the particles are going to move faster. So that's because gases have a lot of energy. So they are moving around a lot and they are literally bouncing off the walls. They bounce off the sides of their container. So as gases are heated, those molecules begin moving faster. So when we're looking at pressure, we're looking at that bouncing of those molecules off the sides of their container. So the pressure of a gas is going to be the force of the outward push of the molecules divided by the area of the container. So when you're looking at this basketball, for example, this is a regular inflated basketball. It has high pressure. It's a normally inflated basketball. But this low pressure one here needs to be inflated. It needs to have air pumped into that basketball in order for it to exhibit the appropriate amount of bounciness of the basketball, right? So these particles will escape through time because usually the containers that basketballs, or the container that the molecules are going to be in, like a basketball or a football or balloons, is going to allow for those small gas molecules to escape over time. Pressure is measured in the unit of pascals. So if you're looking at a graph, for example, that is looking at different types of variables, if it is referencing pascals or kilopascals, that's specifically talking about the pressure. There's two gas laws that we are going to go over. The first one is Boyles Law. So you probably have experienced this before if you have ever shaken a soda can and then popped the tab on it. If you've shaken the soda can, then those molecules have gotten agitated and have increased the pressure, and then it may have spewed everywhere. So Robert Boyles, a scientist who discovered that pressure and volume are related. So the pressure of a gas, when the pressure of a gas increases, the volume is going to decrease. And that also acts in reverse. When the pressure decreases, the volume increases. So pressure goes up, volume goes down. So they act opposite to one another. So just remember, pressure's up, volume is down. And that is Boyles' law. So we have a little example here, and this is similar to the picture that is in your lab notebook on page 9. So you see a little cylinder here. We've got lots of air molecules, these little blue spheres here that are kind of bouncing off the inside of the container. When you have one weight that's added to it, then it's going to be at this height for the cylinder on the inside. So if you increase that pressure, if you're adding more force to it, then that squishes all those air molecules in the same amount of space. And so it squishes them all downward into that small space. Same thing happens in the next example. If you have more weights added to it, that means more pressure, and so it's going to take up the smallest amount of volume. So you can see that as the pressure is increasing, going from 1 to 2 to 1, 2, 3, 4 weights, it's getting smaller, smaller, smaller amount of space, amount of volume that those gas molecules are able to take up. Just like if you take a balloon and you squish on the balloon, what's eventually going to happen? It might pop, right? Because you're smushing and forcing all of those molecules into a confined, smaller area. The other gas law that we're looking at is Charles' law. So Charles' law has to do with temperature. So Jacques Charles found that temperature and volume are related. So when the temperature of a gas increases, the volume increases also. So they act in the same way. Temperature goes up, volume goes up. Temperature goes down, volume goes down. So they act in the same manner. You may have experienced this before in a couple of different ways. So if you look at this example of a balloon, if you've left like birthday party balloons, for example, out in your car and it's been really cold outside, those balloons, like in this picture, they start to kind of shrivel up and they look kind of like this stretched out kind of pattern to them. But usually if you bring it in your house where it may be a little bit warmer, they inflate a little bit more, like they go back to almost normal. Same thing with a basketball, if you like to play basketball. If you have ever left a basketball outside during the winter time, then when you go outside to play with that basketball, then it's not going to have as much bounce to it as it should, because those molecules basically have started slowing down. They're not bouncing off the sides of that basketball inside of it as they normally would. It's not going to have as much pressure. Same thing with tires. If you ever do work with automotive, or you help to check the tires and inflate the tires on a car and that kind of thing, you may have noticed that. Like I notice in my car, the tires pressure sensor always goes off during change of season, like when it starts getting warmer at summertime or when it starts getting colder at winter, because that fluctuation of the temperature is going to cause fluctuation in the volume. So Charles' Law, temperature goes up, volume goes up. Temperature goes down, volume goes down. They act in the same way. And the last thing is looking at this illustration that is on page 9. So this is similar to the cylinder that we were just looking at a few minutes ago, illustrating one of your gas laws. So in looking at the kPa, the kilopascals, and the amount of volume that's taken up for those gas molecules here, you can see how that pressure on the cylinder is increasing. It's pushing down just as if you were pumping up a volleyball or a basketball or football. You're inflating it by pumping up and down, so it's changing that pressure. So we have our little plunger here. As that is being pushed down, as you're increasing that pressure, going from 100 to 200, it's going to change the amount of space that those molecules are taking up. So they're not taking up 1 liter anymore, they're taking up half that space, 0.5, half of the liter that we originally had. And as you continue increasing the pressure, now we've doubled that. We went from 200 to 400 kilopascals. So now that amount of space, that amount of volume has gone down even further. It's half of that. So it's half of 0.5 liters is 0.25 liters. So you can see with the increase in pressure going from 100 to 200 to 400, that's decreasing the amount of space from 1 liter to half a liter to 0.25 of a liter. So you can look at that pattern and be able to make some observations about the relationship between pressure and volume of gases. So now you should be able to answer those 3 questions on page 9 that are related to this image. Thanks, guys. Have a great day.